Welcome everybody to day 3 of the program. And so our first speaker for today is Dr. Ayush Kumar Tewari from Ghent University in Belgium. And he'll talk to us about topics in computational tropical geometry, particularly forbidden patterns in tropical planar curves. So we are really looking forward to it. Yes, Ayush, please.
I think I'm already mic'd up. Is it working? Okay. So, good morning to everyone. So, first of all, thanks to the organizers for this opportunity to present my work. So, part of my talk are some results that are part of my thesis, and some are recent results that I was able to publish. They are on the archive and submitted. It's working. Sorry. Yeah. So just for a brief outline, today I'll be introducing what I'll be meaning about with skeletons of tropical curves, and hence the subsequent problem of finding certain forbidden patterns. So the main problem is about realizability, to understand when certain tropical curves can occur out of the class of all metric graphs. So I'll be talking about that. And then a slight detour to a certain class of lattice polygons that we encountered, which we named as panopticons. And in the talk, I'll establish the relation that they have with tropical planar curves. And then coming back to skeletons again, turns out that these lattice polygons themselves give us a new class of forbidden patterns, which we call big face graphs. And then hopefully by the end, I'll talk about some problems that I've been working on based on this aspect of my research. So just to introduce the problem that we are dealing with is, so a tropically planar graph is a metric graph G, which is dual to a regular unimodular triangulation delta of some lattice polygon P. So we already saw in one of the previous talks this duality between tropical planar curve and a regular subdivision. I'm taking a special class where I'm considering regular triangulations, which are also unimodular. So I'm in the plane. So for me, this would essentially mean that my subdivision is a triangulation, meaning all faces are triangles, but also additionally, all faces are triangles with area half. So this is the special subdivision that I'm considering. And then I'm looking at the dual tropical planar curve. And so this picture that is in the middle sort of encodes the main problem. So you have a lattice polygon P, and this you can see is a regular unimodular triangulation. And just with the duality that we saw yesterday, so just taking the dual to the edges, we see that this is the tropical planar graph. And the skeleton is something which is depicted on the right. And the way this is obtained is by deletion of edges in this tropical planar graph and concatenation of certain vertices. So the deletion of the edges occur with the degree 1 edges, sort of the ones going to infinity. So those edges get deleted. And after that deletion, you're left with degree 2 nodes, which you sort of smoothen out. And with that graph theoretic process, the end result is a planar trivalent graph, which we call a skeleton. And the color coding here represents what I mean by metric graph. So metric graph is nothing but a graph, but with each edge, there's a metric associated. So the color coding here sort of represents the metric, like the length data attached to it. Although for today's talk, I'll be working with just the combinatorial shadow, but one has to remember just for the idea that the whole picture is the graph along with some metric data attached to it. And
so, question. Yeah. So this circles that you have drawn,
yeah.
Should I think of them as self loops?
Yeah, loops in our loops. Yeah, essentially. So that's a vertex, and this is a loop.
Yeah.
Yeah. So yeah. So essentially, the skeleton would be multigraph. So, and so some important terminologies that we want to recollect here is that, first of all, just to recall, tropical curve is dual to a regular subdivision of the Newton polygon. We are in the smooth case, so we are considering smooth tropical curves which are dual to unimodular triangulation. And a very important invariant in throughout this problem would be what we call the genus, which is equal to the number of cycles in your tropical planar graph. And it is also equal to the number of interior lattice points in your lattice polygon P. So going back to the picture, we see that there are 4 interior lattice points, and you have 4 distinct cycles here. And those cycles are also present in your skeleton. So this is sort of the invariant throughout this process. And we'll be working along with this genus. So this is genus 4, essentially. So just to formalize the definition of the skeleton, so each tropical planar curve that we obtain contains an underlying metric graph, genus G, which we call the skeleton. It's a planar trivalent graph with G many distinguished cycles. Also, if you want to see, if you start with genus G, the skeleton is a graph on 2G minus 2 vertices, and it has 3G minus 3 edges. So with that done, sorry. Yeah, sure. So we'll see this picture. It's a bit special. So we'll see this picture later on as well. So when we discuss about particular cases. So yeah. 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 That's the underlying, yeah. But yeah, so I think, yeah, but like I'll be talking about the weights like mostly at the end, just to give you a picture that there's a moduli space of metric graphs. But like the forbidden patterns are purely combinatorial, like graph theoretic criteria. But yeah, one has to keep in mind that there's a metric and there's a genericity that we are assuming here. So yeah. So now just to give a recap of what has been done essentially prior to my work was that in 2015, Sarah Brodsky, Michael Joswick, Bunch Strumpfels, and Ralph Morrison tried to study essentially the moduli space of tropical plane curves of genus G, which essentially just means that they wanted to understand what all tropical planar curves can appear for lower genera, meaning specifically for genus 3, 4, and 5. By analyzing the moduli space of metric graphs. So essentially, so I'll be describing what the method was, but essentially is like you can work around with a finite class of lattice polygons with your given genus. And then you essentially compute all regular unimodular triangulation. Computer software like Polymake can do that easily for you. And since the genus is low, this is not very large. So there are like, for this case, there are like 1,000 regular unimodular triangulations, and one has to keep into account that a lot of them would give you the same genus, like the same graph essentially. So not all of them give you distinct graphs. And this was essentially, so all of this was encoded in the software. So this was a computational study for these genuses. And we'll look at what they did essentially. So again, this is from the paper, as essentially the same essence of a picture. Here you have a unimodular triangulation again, and here you have a tropical planar curve, and here's the skeleton. Again, the color coding just represents the metric data.
Sorry, but this is not a finite process, right? Because the genus is the number of interior vertices. So the exterior vertices can be arbitrarily high.
That's what I'm going to say, that there's a result that says that you are okay with a certain maximal polygon.
I see.
Yeah. So, yeah, sure.
Is the realizability as like or
in the tropical world, like in the plane, I'll talk about like realizability. So in R2, you can embed these curves in something called as a modified tropical plane. So then this problem becomes of embedding in the sense of what you're talking about. So here we are just embedding these graphs in R2. So what you can refer to as the usual tropical plane. So yeah, at the end I can point to some recent work where they have worked on taking like modifications. Mm-hmm. So realizability for me here is about the skeleton, because that encodes all combinatorial information. So when I talk about realizability, I'm just looking at the graph. Obviously, when I say realizability, it means it's coming through this process. So obviously there is a tropical planar curve attached to that. So yeah, so just to answer the question that, okay, how are we going to do this for a certain genera? So this is one paper by the same name by Castrick. So that is by the name of Moving Out Edges of a Polygon. And in it, he classifies a certain class of polygons, which he calls maximal. So I'll just explain. And in that, he uses this result of Coleman's from his PhD thesis. So the thing to start with is, let's consider a lattice polygon. So I'm just using his notation. So he uses delta here, although I'm use P for a lattice polygon, but just for the time being to stick with his notation. So this is a two-dimensional polygon. So you can consider the convex hull of the interior lattice points, and that you call as delta 1. And then the process of moving out edges is just that you consider the hyperplane that gives you the edges of your polygon. And then you just add 1, like ax plus by is equal to c. That's your hyperplane. And you just add 1 to c to move out the hyperplane by 1. So that's what -1 refers. So like you can, here it's delta 1, but you can just take delta -1. So -1 just means adding 1 and moving out the edges. Obviously, it's clear that moving out in such a way of a lattice polygon may not lead you to a lattice polygon. So it's not necessarily true that if you move out edges of a polygon, you always encounter a lattice polygon. But this is a nice result to begin with, which says that if you start with a lattice polygon, consider the convex hull of the interior lattice polygons, and yeah, so it's a way to conserve direction. So if you're taking minus, then you have to take like, you're taking the minus.
So his question is A
Yep.
plus B by
Yeah.
C.
Yeah.
also
Yeah. So in that case, he's taking like the minus that I took. So it's the idea is to move like away from the interior. So the thing is, like, adding +1 or -1 are the only two cases. So that's one way to do that. That would be my answer. But I think because okay, I think that's one way to do it. But because it's adding +1, so you're either moving outwards or inwards, in the sense of like moving your edge out. So that's the only two possibilities. And this, if I pick the standard notation, then I just add +1 and move up in that sense. Yeah. Yeah, for the time being, you can consider that. But I'm not scaling in any sense. I'm just moving out. Yeah. Yep. Yeah. Yeah, but I'm not scaling it in any sense. I'm just taking the facet, the hyperplane defining the polygon.
No, he's taking GCD1.
Yeah,
You have
yeah, he said that.
You're adding half.
Yeah, exactly.
So no, but yeah, okay.
Okay, so essentially, in this special case, what happens is if you start with your poly to consider the interior convex hull of your points, so that gives you a polygon, and then you move out the convex hull of the interior lattice points. So that he proves that polygon that you get always contains the polygon that you started with. There's a containment. And you call a lattice polygon maximal if it's exactly equal to this. So there's a containment, and then you classify this when it is equality. So those are essentially the maximal ones. So Coleman proved this, and in this paper, Castrick gives like a list of all maximal polygons given a genus, like number of interior lattice points. So it's a computational enumeration for up to genus 30. You have a class. So this is already done in 2012. So this is exactly what they are going to use in. No, No. So there is no notion of moving out in dimension 3. This is, okay. So this is a spoiler. So we are working on it. So just to, yeah, so no. So just to give you a recap of what was done in the 2015 paper. So this, for again, from the work of Castrick, we know that for genus 3, this in the Maxent polygon, this is the unique case, the standard triangle. So this, you just need to consider this one and compute all its regular unimodular triangulations. Yeah, here regular means unimodular, like I have missed unimodular, but for me, regular triangulations are all like unimodular in this case. Again, we also have an enumeration of all trivalent graphs given certain vertices. So this is from the 70s. So we know that on 4 vertices, these are the 5 non-isomorphic graphs that occur. And now we want to, and the subscripts are just to give you the idea that it's a metric graph. So, but for us, for the time being, it doesn't matter. The numbers here is a way of encoding these graphs, and these represent like loops, bi-edges, and cut edges, just the way of notation. So like here we have one loop, so there's one, and a bi-edge is like this. This is a bi-edge, this again is a bi-edge. And the last index represents the cut edges. So here we have a list of all such graphs, and we want to understand out of these, how many can occur by considering regular unimodular triangulation of the standard triangle, computing the dual tropical planar curve, and doing the graph theoretic process to get the skeleton. And turns out that the first 4 do occur, but this one doesn't. So this is what they noted for genus 3. So this was all computational. So this is just enumeration of that. So again, for genus 4, you start with, again, going back to the list of maximal polygons, you see that these 3 are the ones that are needed for genus 4. Just to give you a census of what we are dealing with here is, so not so bad still, so doable. So,
sorry, but
yeah,
you didn't explain how these suffice.
Yeah, so that's a result of Castrick. So considering all, he talks about like dual graphs.
Yeah.
So he's not talking about tropical curves essentially, because it's from 2012. But he shows that all dual graphs that can occur for a specific genus or interior lattice points is equivalent to considering the maximal ones. You won't get any new if you start with any other one.
Okay, thank you.
So essentially saying,
but it's a non-trivial result.
Yeah, it's a non-trivial result. It's a non-trivial result. So the thing is like, so this 2015 paper was, so Castrick proved this moving out edges polygon. Then they did another paper in which they studied like a classical modelized space of smooth curves over a field of non-Archimedean valuation, and a little similar to this, but classically. So that's where the inspiration came from, that, okay, this works classically, then we can take that study and work around and work tropically to understand. And there's a way to go back and forth, which maybe if time permits, I can discuss that as well. So again, for genus 4, we also have enumeration of all graphs occurring on 6 vertices. So again, here we have 17 such graphs. This one is non-planar, so we are considering planar, so you can, so non-planar is also like a trivial criteria that you can take that graph out. And in their computation, they again saw that the graphs marked with the asterisk, these do not occur. So these 3 do not occur. And so yeah, so just to mention what is happening here. So they already saw in that paper, so they gave the first criteria here. Maybe it's better to explain it here. So they call a graph sprawling if there's a vertex which is attached to 3 cut edges. So this graph is sprawling. So in their paper itself, they gave this first criteria of a graph not being able to occur as a sprawling triangle. So this was one of the first criteria. And the proofs are just by convexity, nothing non-trivial, invoking convexity and using the fact that you are dual to a trivalent graph. So you have triangles and arguing that. So nothing very spectacular about that. So this was, so again, here you can see that you have 3 cut edges here, here, and here. So these 3 are sprawling, that one is non-planar. So in this, so up till genus 4, you could only work with like the forbidden criteria and just remove out the graphs, and you don't even need to do the computation and enumeration. They were complete in that sense. They did it anyways, but up till genus 4, it was complete with these two criteria, non-planar and sprawling. That was good enough. But what was not good enough was genus 5, but just as a detour of some sort, I just want to mention that troplanarities, again, troplanar graphs are realizable graphs, another name for it. So just to mention that it is not minor closed. Essentially, we saw this graph, obviously, in the first slide, and this is realizable. But if you look at this minor, this is sprawling. So because one has an idea that, okay, if we find like a forbidden minor class family, then it would be a great way to classify this, but apparently it turns out that it's not the case. So just to give you an idea of what was done prior to our work was this. So we obviously saw sprawling. So the shaded areas represent subgraphs of positive genus. So this is one instance of a graph being sprawling. Then the other class is a bit non-trivial to define. So this is, we call a graph crowded if for all its planar embeddings, there's a face that either has a edge intersecting with itself, or there are two faces that share two edges. So this face and this face share two edges. A bounded face shares a face with itself, and this should happen for all planar embeddings. So this is like, not all crowded graphs look like this. This is just one family. The other one, yeah. The other one, if I can recall, is something like a I think it's this maybe, but no, these are two faces. So there is an example, but I can't recall it right at the moment, but it's important. There are examples like that. Yeah, so yeah, just to recall. So like just the faces here in the embedding, like for this example, there are two faces that share an edge. The other one is if it intersects, I think, okay. The face has an intersection with itself. Okay, so I'm like, there is another like two conditions, but I'm right now not able to recall exactly what that is. But like, this is one condition showing by the example, but there is one another. And so that's crowded. It's a bit different from any, like, this is a unique criteria. It doesn't involve any cut edges. So, and the proof techniques are also a bit different. And apart from that, there is also another criteria called the TIE-Fighter, which is sort of self-explanatory. So your graph has to look like that. So any Star Wars fans would get the reference. So it looks like a TIE Fighter, and there are like shaded portions, again, represent subgraphs of positive genus. So these were the criterias that were known prior to our work. So again, some things that we will be using again in our work, just to explain them. So a split is a subdivision which has exactly two maximal cells. It is always regular. So one can think of the split as like sort of a counterpart to triangulations. Triangulations are really fine, the finest subdivisions, and splits are the coarsest, in some sense. So one important thing that Ralph Morrison in one of his papers noticed, that cut edges in your skeleton correspond to splits in the unimodular triangulation. And two such splits are compatible. So obviously with a split, there are two maximal cells. So there's a split hyperplane that defines actually that subdivision. And two splits are said to be compatible if their split lines do not meet in the interior. So there is a notion of compatibility. One nice thing that happens in our case is that splits corresponding to distinct cut edges are compatible. So maybe just to show what this discussion was, it's good to go back to the picture. So here you can see that this edge is a split. If you forget all the other edges appearing in the subdivision, this edge in the triangle is a split. This edge in the triangle is a split. Like you negate all the edges appearing in the subdivision and just take this edge. So you'll get two maximal faces, one this quadrilateral and one triangle. So this defines a split. Again, if I just consider this edge, then I get a triangle and a quadrilateral. Again, this one is a split, and hence likewise this is a split. And they are all compatible since the hyperplanes do not meet in the interior. This is very nice. And they are non-trivial in the sense that the subpolytope that you get has positive genus. So you can get like trivial splits that just are a triangle and you don't get a polygon with a positive genus. So this is essentially the crux of the argument that we'll be using in defining criteria, is essentially these cut edges, this appearing in the subdivision. So the first, so this is not a criteria in itself, but it's sort of a structural result. So if your graph looks like this, then we say that it has a heavy cycle referring to this cycle C. So all graphs here, shaded regions represent positive genus. And we consider like this polygon that realizes this part as P prime. So let's say we have a graph which has this structure. Then the triangular faces, so each vertex appearing here in the skeleton is dual to a triangular face in the subdivision. So there are the triangular faces T1 and T2. Then they actually share an edge. That's what this structural result is claiming, wherein we even know the points that are there on the shared edge, that shared edge being Z and W, Z being the interior lattice point, which is dual to this cycle C in the subdivision. And W is the point of intersection of the splits because we have cut edges here. So these would correspond to splits. And another implicit point here is that the vertices of a split edge in the subdivision reside on the boundary always, which is the case here. So W is the point of the intersection of these compatible splits. And again, that's the same thing, that the split lines intersect in W. And this is the structural result. So just to give you a brief idea of how the proof goes is like we take a contradiction and assume that the two triangular faces actually do not share an edge, but they do share in vertex because they are part of the same cycle C. And then we consider the two cases where the split hyperplanes are parallel or they intersect at a point. And we get a contradiction in both cases. So hence they have to share an edge. So using this, using that structural result, one can prove a criteria, which is essentially what we call as the sprawling triangle. So we say a graph has a sprawling triangle if it looks like this, where you have a triangle attached to subgraphs of positive genus like this. So this is the first criteria that we were able to show, that for genus 4, the graph that we saw in the first slide is actually a graph with sprawling triangle, but that is the only realizable graph with a sprawling triangle. So that is the case. If you start going above genus 5 or above, then you don't encounter a graph that can have a sprawling triangle. So this is one of the first new criteria that we were able to add. Again, the proof is similar, invoking convexity and using the fact that we have something like a result like a heavy cycle and the compatibility of all these splits. So even in the picture, just that's one of the speciality of the picture, that you see the splits are compatible here in all of that. And this triangle is uniquely, like this triangle encodes the sprawling triangle that appears in the skeleton. So yeah, going back to sprawling triangle, and we were also able to find, I'll be talking about these special triangulations later on. So this instance of this sprawling triangle can also be generalized to certain higher class of triangulation, which we refer to anti-honeycomb. And there's a reason for that name as well. But yeah, so I'll be talking about them later on in the talk. So another criteria that we were able to come up with was when we consider two loops attached. So earlier in the heavy cycle lemma, we had these graphs of arbitrary genus, but now we fix them to be loops. So there's just one interior lattice point. So it's easier to argue. We are working with in the subpolygon, you can argue that there's only one interior lattice point. So what we show in this result is that, first of all, the subpolytope that realizes this cycle along with this subgraph G3 has to be hyperelliptic, meaning essentially that the interior lattice points lie in a line. So the interior convex hull. So in this terminology, there is hyperelliptic polygons and non-hyperelliptic polygons. So hyperelliptic polygons meaning that the convex hull of interior lattice points is one-dimensional, meaning they are on a line. And non-hyperelliptic is just that the convex hull was two-dimensional. So that the moving out stuff is only for non-hyperelliptic polygons, so not for the hyperelliptic ones. So again, just to recall, so this result just talks about that if you have a graph with a heavy cycle and two loops, then the subpolytope realizing this part has to be hyperelliptic, and the total genus of your graph cannot be more than 5. So in the proof, we use the heavy cycle lemma. So now we actually know that the two triangular faces actually share an edge. And you can start with such a condition. And then one can argue, since you're working with just one interior lattice points, you can sort of argue that this R has to be if you fix this triangle in this position, then this R has to be that unique interior lattice points. And likewise, this R prime. And then invoking convexity at these points P1 and P2, you see that the only position for the interior lattice points is along this line. And one can also argue that this point can never occur, which is like the fourth point. So this genus is bounded above by 3, and hence the total graph can only have genus up to 5. So with these two criteria, we were able to push the result that was done in 2015 to the case of up to genus 5, and there's no computational enumeration. So we were able to provide a complete list of obstructions, which when negated, the list of graphs that you're left with are all realizable. And since this list was computationally known prior as well, so this matched with their computational results. So again, just to list it out, the obstructions that can occur is like obviously previously known sprawling node, or a sprawling triangle, and genus being at least 5, or it being crowded, or it being a TIE fighter. These were all prior known. And the last one that we added was a heavy cycle with 2 loops. And again, arguing that the interior lattice points of the heavy component, again, just stating that subpolytope has to be hyperelliptic, meaning all the interior lattice points have to lie on a line. So we had a complete, so around, if I remember, there are 71 graphs for genus 5, out of which these 4 were left to be categorized. So these 4 can be eliminated by our criteria, these 2 by the sprawling triangle, and these ones are heavy cycle with 2 loops. This one can argue this subpolytope is not hyperelliptic. And this one, it is hyperelliptic, but it is not in the prescribed direction. So this is like, they do lie on a line, like they can lie on a line, but not in the desired direction that we want. So hence, these graphs cannot occur using our criteria. And there were like around 28 graphs left to be categorized for genus 6, out of which, using our criteria, we could reduce it to 8 graphs, which look like this. And in our paper, we left this discussion up till here, that we complete the picture for genus 5, and genus 6 is left with these 6. So this was till 2020, and then I was able to push some of the results to genus 6, one of them being just taking the case of heavy cycle, but with 1 loop, and considering the other one to still be of arbitrary genus. So now the result is just a bit more intricate, meaning that, again, we get a total bound on the graph. This, again, has to be hyperelliptic, but the total bound on the graph is 7. So such a graph cannot be realizable for genus greater than 8. But we wanted something to say about genus 6. So in that case, we were able to show that for genus 6, if this subgraph has this genus 2, then it has to be hyperelliptic. And the triangulation restricted to this subpolytope cannot have a non-trivial split, meaning again that the 2 points cannot be subdivided with subpolytopes each of genus 1. So one good example to look at would be like this. So ideally this graph should be upside down. So this genus 1 loop is being realized here, and this split is the cut edge here. And you get sort of this long split corresponding to this cut edge. But that's it. You can't have in this subpolytope, you can't have another non-trivial split such that these 2 points also get subdivided. So hence this component is realizable, this genus 2, but there's also just one other possible component, which is like a loop attached to a bi-edge attached to this cut edge. So that is not realizable because in that case you have another cut edge for which there would be a split required in this subpolytope. So that, yeah, so this split, this edge, this in between. So yeah, I'm sorry, like you need to enlarge this. Yeah, so essentially you can see this happens, this edge joining this and this boundary vertex. Maybe I'm not, between this edge, this point, sorry, this point and this point, that edge in between. The other one is the triangle, this one. So realizing this cut edge here. So you can see here that the list that we have here is essentially all like the cases here do have that cut edge here. So that's why they're not realizable. You have 2 cut edges here. So essentially, that's what we saw in this case. And we were also able to show like structural results similar to the heavy cycle, but now they are, call it the double heavy cycle. So in this case, you have 2 such cycles. And in the heavy cycle, we just showed that the triangular face dual to this vertex and this vertex actually share an edge. And that property is just now extended in between these 2 triangular faces. So these 2 actually now share an edge in between each other. So that is just essentially the crux of this. So it's a usual generalization of what you would expect for the heavy cycle. And likewise, a counterpart, meaning that if you have a graph, now we consider double heavy cycles with 2 loops. So now we were not able to like claim a general criteria for like bounding the genus or something, but we were able to show that if the genus is exactly 6, then the interior lattice polygon of this, what we refer to as the heavy component, this subpolytope, has to be a unit parallelogram. So that restricts in some ways what cases can occur. So using these 2 criteria, we were able to push our results to genus 6 with just 1 graph left from those 8 that we saw the picture here. So this one. So for the time being, I've named it as NV loop because almost an envelope plus a loop. So if somebody has a better name, then you can let me know. So because, and I assume that, so what's happening here is like the cut edge is only 1. So then these sort of arguments are tough to extend in that sense. So like something, and it has also come into our study that there's a sort of distinction between arguments, between graphs which have less and less cut edges. The arguments needed are very different from what we are referring here. So like one of the such forbidden criteria was crowded. And I'll also talk about one criteria which doesn't involve cut edges later. And you will see that the arguments are a bit different. So yeah, so apart from that 1 graph, this is the list of obstructions. Obviously, it's a bit loaded in that sense. There are a lot of obstructions, but essentially the same ones repeat. Some of them like sprawling nodes, sprawling triangle, crowded, TIE fighter, recycle. And there's one additional one which wasn't needed in the genus 5 case because everything was complete, but was priorly known. Like this is not something that we showed, but it's essentially the same argument for the cut edge. So like if you have a cut edge, the components that you get should also be realizable because the split is regular. So you can like restrict your subdivision to one of the components and they have to be realizable. So that is needed for negating some of the graphs. And then if you add the two criteria that we discussed in our work, then you are done, except this graph. So, and just as a detour, as I mentioned, because I used the name Anti-Honeycomb, so you can sort of generalize the picture. Maybe I'll not go back, it'll take me a lot of time. So just the picture that we saw in the genus 4 case. So if you look at this triangle here, this triangle here, that was again the genus 4 case, just a bit rotated. So you can sort of generalize the really nice triangulation that we got and to higher genus. So this is like a genus 19 case. And you get it by these class of lines that you define. And the name is coming from something. So there are certain honeycomb triangulations. So as you would expect, the dual skeleton has like these hexagons together, so which looks like a honeycomb. And that is also a bit special that that it encodes like to each this triangulation. There's an underlying dimension of the moduli space, which is attached to the metric data. And the honeycomb triangulation sort of achieve the maxima. So like, as I mentioned, the skeleton is a graph with 3G minus 3 edges. So the space that you're living in is R to 3G minus 3, where you're attaching metric to each edge. But it turns out that if you're coming from this process, the dimension is much less. It's only 2G plus 1. And the 2G plus 1 is supported, the locus is supported by honeycomb triangulations. So that is like the metric data and the idea behind this, because so honeycomb achieves the maximum dimension, and these sort of, there's not the minima, but towards the lower side. So hence sort of a counterpart to a honeycomb triangulation. So is yeah, that's a result that they show in Joswick's initial paper, that it's actually 2G plus 1, but 2G plus 1 for genus greater than 7. For lower genera, it's not according to this 2G plus 1, but it's lesser than that. But after genus 7, it's well behaved and it's actually 2G plus 1. Yeah. Just exactly. I think in your paper, this tropical immersions, you actually so I'm just showing combinatorial obstructions, but there are metric obstructions. Like there is this theta graph for genus 2. So I started with the genus 3. So there's this, for genus 2, there is this theta graph, and a metric obstruction is that A is equal to B is equal to C. That metric is not possible on this graph. So that's like a metric obstruction. So, but now I'm not talking about metric obstruction, but that is essentially the case. No, they are not like, this study is not like if all the metrics that you remove, then the dimension is exactly 2G plus 1. If you're arguing that, no. This is not done in that sense, that okay, I compute a list of non-realizable metrics and then just negate it out of my fan and I get 2G plus 1. So yeah. So now a slight detour to a classification of certain class of lattice polygons, which we named as panopticons. So yeah, it might look like that, okay, a new talk has started, but just give me 5 minutes and I'll connect it back to what I was discussing earlier. So a panopticon is a lattice polygon P, such that it has a point small p, which can see all of the lattice points in P, or all other lattice points are visible. And we call the small p the point as a panopticon point. So these are the examples of certain panopticons. Panopticon, okay. Oh, okay. Yeah. So so I think panopti in panopti, I think in Greek means all seeing or something like that. Yeah. Opti means, yeah. Yeah, actually the thing was, we called it panopticon. Then somebody in one of the talks said it's a polygon, so call it gon. Yeah. Like if you Google this right now, you'll get something not related to this. You'll get a music player or some company. So we are thinking of changing the name maybe at some point. So these are the examples of panopticons, and the point encircled is the point that sees everybody. And obviously, by definition, it's not unique. You can see that this point is also seeing every other guy. And I would also like to just show that here, that if your lattice polygon is really thin, which I'll make it more precise, then you can have like infinite points. You can just extend this strip essentially of lattice width 1, and then you can just fix this point, and it will see every other point on this line. So in order for a like finite enumeration, which we actually did, you need to consider like a constraint on your lattice width. So lattice width is like you consider all possible directions, move lattice distances, and then take the minima out of all such directions. So what we saw is that if you consider this presumably very lax condition, which is of lattice width at least 3, then the panopticon can only have at most 13 lattice points. So this is very hands-on. So essentially we fix the origin, and there's another implicit parameter that we are using here. It's called the lattice diameter. So it's the longest lattice line segment. And we also sort of fix that it's at least 3. So, and then we complete the picture by taking the other case where the lattice diameter is at most 2. So that parameter is not as significant as the lattice width, at least being 3. So you fix the origin, and the black dots represent the points visible, and the crosses represent that the points are not visible. Then using convexity, you can sort of argue that these families of points shaded by the green area cannot occur in your polytope, but you're still left with a lot of black points, and you can't just still like considering any combination of this enumeration would be too long. So there are added conditions that, okay, if you choose one point from here, then you have to be below certain hyperplane and stuff like that. Essentially, with these arguments, you can reduce and actually enumerate all of them. So I'm sorry if the picture is, this is the most optimum way to like push all of them in one slide. So essentially, yeah. So these are all the ones that you can see, and the encircled point represent the point that sees everybody. Non-hyperelliptic is another way of saying lattice width at least 3. And again, I was saying that there's an implicit parameter of lattice diameter at least 3. And just to complete the picture, so LP is the lattice diameter. So again, taking the case when the lattice diameter is at most 2, then in that case, we can easily enumerate all the rest of the ones. And there's also like, given a lattice diameter, there's also a result to bound the number of lattice points. So we already had the argument for that for this case, the number of lattice points cannot go beyond 14, but just in order to complete our enumeration, we also, up to unimodular equivalence, showed what they actually look like. So yeah, so this was one enumeration. Then what connection does it have to the discussion that we had earlier? So for that, we define a new class of graphs, which we call big phase graphs, such that for any planar embedding, there exists a bounded phase that shares an edge with every other bounded phase. So this family of graphs we call loop of loops for a given genus. You can see there's a central phase that shares an edge with every other phase. And what turns out to be the case was that for such graphs to be realizable, the interior convex hull has to be a panopticon. And for that to be a panopticon, we already know the bound on the number of points. That is essentially the genus. So in another language, it's just saying that such graphs can only be realizable up to genus 13. So just to show that what might the triangulations look like, they look like this. So again, one of the sort of extremal cases, the genus 11 case, you can see this is the triangulation, and this is a big phase graph. And so with our enumeration, we were able to show this criteria. So if you have a big phase graph of genus at least 14, then that graph is not tropically planar using our case. And this bound can also be bettered because we have a complete enumeration. So we can sort of start moving out the ones with 12 or 13 and see if they are even lattice polygons or not. And if that's not the case, turns out there are some which are lattice polygons, but at least in any case, we get this bound. And so, yeah, so this is another, so this is one instance which where there is a criteria which doesn't involve any cut edges. But as you saw, the arguments and the way we landed on to this is not similar to the discussion that we had. So this is some problems that we are working on right now. So generalization of panopticons. Turns out it's not similar to that. So there's some sort of luck also going on. So we talked to some people who are into this lattice point enumeration. So this is not the most optimized way of like searching for all polygons, but rather look for maximal polygons and classify that. That turns out to be the case because this is computationally much harder than the dimension 2 case. And with a slight argument, you can look, we can change this enumeration to actual enumeration of hollow polytopes, half integral hollow polytopes, and special polytopes which just have one unique interior lattice point. So they are also referred to as canonical Fano polytopes, like people interested in Fano varieties have done some enumeration. The thing is, we are interested in half integral polytopes of such enumeration. So there is an enumeration of hollow polytopes in the lattice Z, and up to some volume constraints. So the constraint that we used here, lattice width and lattice diameter, are replaced by volume constraints. So that's what we are working on currently. We have some examples of like these maximal ones, but this list is not complete at this point. So we know that there might exist more. So at this point, I can show you just some examples, and this is currently what we are doing. And as mentioned, I think somewhere in the talk, the question was asked, so again, this notion of moving out. So this notion of moving out is essentially described for dimension 2 polygons, but we want to understand that for dimension 3. And essentially, with hopefully a nice definition, we can also extend the argument of Josvig, the whole analysis to dimension 3, because we can compute regular unimodular triangulations and look at corresponding surfaces. And again, the realizability question still is relevant, but now you have a different notion of a skeleton or like likewise. Also, there has been some interest for people coming from chess. So in chess, like a move is apart from the knight, I'm not considering the knight here. So yeah, so visibility does play a role. And and you can consider the chessboard as a lattice. So then you can ask certain questions of certain moves, might be interesting. And then we also encountered some questions about lattice visibility. So we just, it was serendipitous. We just encountered, we thought such polygons might have been enumerated and we'll just use it for our tropical results. But since we have been reading about lattice visibility, this does show up in like number theory a lot. So just to give you an idea, I think Gauss circle problem is there, which is not lattice visibility per se, but it can be modified. It just asks that if you are in the lattice at the origin and you consider a circle of radius r, then how many lattice points are in your circle? So roughly it's pi r square, but then there's an error term on which people work. And there's also like if you are in the n cross n square lattice and you are at the origin and you want to pick a point at random in your square lattice and want to ask whether it's visible or not. So the probability is 6 by pi square. So like number theory stuff comes in. So there is a lot of stuff just concerning lattice visibility, maybe not with convex polygons, but in other shapes like circles or whatnot. Yeah, exactly. So you can modify that argument, but for that you will need like how many points are there in total? So that is like Gauss's problem, but now we have some error term. So yeah, then you can ask for like how many out of these are now visible. So that's one of the problems that we want to understand. And then there has been some interest in understanding So maybe I can mention that. So as I mentioned about the metric structure, so that actually has a fan structure, which is called as a stacky fan. So with each edge, you have associated a length, but then you sort of glue together your cones modulo the graph automorphisms. So you don't want to count the same metric length for the isomorphic copy. So this gives you a certain space called as a stacky fan, and people are interested in understanding the topology. So for that, for lower genera, turns out that this forbidden criteria analysis is important. So as to look at graphs of a certain class, let's say sprawling or ones with sprawling triangle, and then look at what might be the topology associated to it. So that stratification of this family of graphs helps out in that analysis. So we want to understand that, and like it's very recent. So some progress has been made for genus 4. So I think that's what I wanted to talk about. These are some of the references. So this one is one about the forbidden patterns, and this one is the one about panopticons. And this is the recent one with genus 6. So yeah, thank you. That's it for me.